Hello, WVU Research Symposium. My name is Spencer Renier. I'm a mechanical engineer, and I'm doing research under Dr. Gu at WVU's Interactive Robotics Lab. Today I'm presenting my research, which is a novel solution to inertial measurement unit, or IMU, location drift during long-distance traversal. One of the most important jobs autonomous mobile robots have is localization. Put simply, localization is finding where you are in relation to what's around you. Getting lost is the most dangerous challenge autonomous robots face. Being lost can mean mission failure or even threaten robots' overall well-being. Just about every piece of modern technology has the ability to localize itself. Most devices, including your cell phone, has two things: inertial measurement units, or IMUs, and global positioning systems, GPS. IMUs use a variety of sensors, such as accelerometers, gyroscopic sensors, and magnetometers to determine the device's orientation, speed, and direction. GPSs, put simply, are able to find your position by using 3 or more satellites to triangulate your position based off of your distance from them. Used together, both GPS and IMU use each other's data to cross-reference and verify that you are where they think they are. Problems begin to occur when you operate outside of the reach of GPS, such as on Mars, and need to be able to rely on your IMU alone. Localization with only an IMU can be done by piecing together velocity and direction data taken at regular and frequent intervals. Through this, approximate position relative to where you are can be given. In order to get your velocity and position data, you need to integrate your raw acceleration data coming from an IMU. Doing this at said regular and frequent intervals, you will generate noise, potentially biasing it and making its estimation much less reliable. Letting this run amok can almost guarantee the robot's loss of position. Luckily, there is a solution. The error generated can be virtually eliminated through the process of a zero velocity update, or ZUPT for short. This takes place when the IMU is at a known state of zero velocity, so when a button is pressed or an external action is taken to confirm that the IMU is stationary. The data being output from the IMU above or below zero is used to recalibrate the IMU and find true zero. The picture here actually comes from a PhD proposal from one of the students here in the Interactive Robotics Lab who put an IMU in their shoe. They found that they were able to gather very accurate pedestrian tracking data as the ZUPT took place every time they took a step. The goal for my research was to find a mechanical solution that would provide a zero velocity update on a moving autonomous robot. So I was more or less trying to recreate the walking ZUPT experiment just on a less frequent basis, like once every few minutes or up to an hour. In terms of requirements, I had to deploy a secondary IMU onto the ground and hold it still as the robot drove past while getting position sensing feedback from another sensor, or just another redundant sensor that would approximate the velocity during the ZUPT. It had to be mechanically robust, so it had to be simple, with minimal points of failure, and had to be able to take impacts from random terrain features at fairly slow speeds. It also had to be compliant, so it was supposed to rely on non-powered systems in its homing sequence and as it moves with the robot. Finally, it had to eventually fit within a 14 by 11 by 11 inch cavity in the center of one of our existing robots. I had a variety of initial ideas and inspirations, but these were some of the top ones that I actually did not end up doing. The Cartesian one here on the left was based off a 3D printed design and was almost entirely powered. It had no compliance and used a variety of motors. It also took up more internal real estate than was realistically available. The arm idea was really interesting and could be very diverse in its use, but found it was overly complicated in the system and didn't have any compliance. It also wasn't passive, meaning it required actions or an actuation to keep it on the ground, which made me worried that it would influence the movement of the robot, which we were trying to avoid. Finally, the Delta, which is also based off of 3D printing, seemed like it would work well, but once implemented into CAD, found it was much bigger than I realized and needed at least 3 actuators and had the smallest range of motion out of the 3. So here's the initial design that I did end up going with. It's designed around the idea of a joystick in that it reads an X and Y rotational position and moves in a ball joint. Because of the ball joint, it has a very wide range of motion and is very mechanically simple. The image on the far right was the initial geometric mock-up I made to see if it would fit inside the space, which it did. Then came the ZUPT payload. Here it's split into two major sections. The piece on the left is the central carriage that is pulled up and down by a winch-like motor affixed to the outer supports on the right. The carriage slid up and down on the T-slot rails using Teflon linear sliders that kept it in line. The carriage assembly is further broken down into two ball joints, one at the top, one at the bottom. The top housing, the locking mechanism, as well as the encoders, used to read the change in angular position, which can be turned into an average velocity. Below that, the spring-assisted minor linkages connect to the encoders to the main linkage, which then connects to the secondary IMU on the end. So here, you can see on the left the fully assembled ZUPT payload, and then its method of deployment, in which the winch lowers it down, and once touching the ground, the IMU is then able to move laterally. And then on the right here is a simple diagram showing the encoders finding their initial position and final position, which is seen through the angle theta there. By getting the initial and the final, we can calculate the distance A it has traveled, and in a set amount of time, we can find the average velocity. So here's a video of just a general test, system test. So here I hit the button, deploys and hits the ground. I move the payload to simulate the robot driving past, and another button to retract it back into the robot. Now these are ideal conditions and then pretty slow speeds, but this does demonstrate the general mechanics of the system. Sorry about that. Here's a closer look at the IMU and its green protective casing as it comes in contact with, this is a beanbag here filled with small rocks. It makes initial good contact, but then as the payload is moved above, the IMU sensor here in green actually moves. And I'll play the video again here in just a moment. And you can see that because it's moving, this test is a failure. The goal of this robot of this mechanism is to keep the IMU in place as the robot drives past. So here, we'll watch it one more time. Good placement. Payload moves and the IMU moves. So it was a failed ZUPT. And here's another look. This is actually an unexpected outcome of the test here. You can see the IMU is deployed and it is deflected off of the black case here. This is probably a failure because it seriously reduces the range of motion that the robot can move, as well as unintended movements to the IMU. It was just a very interesting outcome that needs to be addressed in further iterations. So, in conclusion, it had some successes. It had rapid and consistent deployment and retraction. It was compliant in that it could home itself without the use of powered systems, and it was robust. I didn't have any mechanical failures, which is really great to see. On the other hand, it did have some seriously significant failures. It had poor ground compliance, so it really couldn't conform to non-flat ground, and the IMU did move during some payload traversals. Not all of them, but some of them. So in payload overall, the payload was not successful in its current state and revisions are needed. Speaking of which, future work, version 2 here on the right is designed to overcome a lot of the shortcomings of the initial version. It's a heavier IMU assembly, which makes it harder to move, especially in the situations of loose rocks and soil. It's going to feature a larger ground contact, which helps it to adapt to more aggressive features such as the black case. It has a wider overall, so it has a much greater range of motion, which means it can be used at higher speeds, the robot driving at higher speeds, that is. It has the implementation of a ball joint lock. You can see it there at the bottom. I didn't get a chance to implement it on the current version, but this locks the IMU in place once it's dangling below the robot. This version makes it mountable on top or on board one of the existing robots. This was not a feature of the initial version. This also features a new winch assembly. This puts the motor out of plane and uses a pulley system that you can see there on the top. This gives the carriage a larger vertical throw, which makes it more adaptable to different situations. I'm also not opposed to new endeavors, so revisiting old designs or coming up with new designs. The ARM design has some feasibility if we're willing to make sacrifices. So acknowledgements. Thank you to the SURE program and in collaboration with the LSAMP program for supporting my research and my funding. Thank you to Dr. Gu, Jonas Bredu, and Dylan Covell for their continued support, guidance, and technical help. Finally, thank you to the WVU RU students for keeping me company. Any questions, comments, or concerns, feel free to put them in the chat or shout them out. Thanks so much.